All right, in theory, we're live. Hey, everyone. Welcome to Open Space. How is it going? So it turns out I was a little confused about my interview with Avi Loeb. It's coming up next week during the weekly Space Hangout. I thought there was going to be two, but it turns out there's just one. I was like trying to find the other one in my calendar, and there's just the one. So I'm going to be interviewing Avi Loeb during the weekly Space Hangout on the 17th of February, which is after next week is the producer of Stargate, the showrunner for Stargate, which is going to be awesome. I'm so excited. In fact, I've been rewatching Stargaze as a sort of as a way to get myself back sort of up to speed. And the show totally holds up. It's great. I've heard there's a new version of Babylon 5 too, so I'm pretty stoked to whenever that's going to make its way onto whatever streaming service that I use. And boy, The Expanse was so good. The finale was, I mean, it's the best season of the best show. It was so good. It was so good. Oh man. Anyway, yeah, hope you're all doing okay. So I think we're starting to get the hang of this now. We did I released the last week's episode today. I'm trying to think of like what's a good day to release it. Do I release it a week later? Chad needs a couple of days. He probably needs till about Wednesday, Thursday. Like if we record on Monday, he needs till about Thursday, usually Thursday or Friday that he's done the editing. And so I'm just trying to think what's the right day to release it. Do we release it on the Mondays? Just like we, but 1 week delayed. Anyway, we'll figure it out. All right. So let's get into this. Hello, everyone, and welcome to the Question Show. Your questions, my answers, wherever you are across my channel. Just go ahead, type it in. I'll gather them up and I'll answer them here. I record this show every Monday at 5 p.m. Pacific. So come join me live on my YouTube channel. And if you're watching this afterwards, I recorded this episode on Monday, February 8th, 2021. So first, some upcoming events. So like I said, on Wednesday, February 10th, our special guest on the Weekly Space Hangout is Joseph Mallozzi, the showrunner for the Stargate franchise. And the week after that, I'll be interviewing Dr. Avi Loeb about, Oumuamua, alien solar sails, and the delicate balance of science outreach. We had a lot of great questions from last week, so I wanted to start with a few of them first before going into the live questions. Let me find my list. All right, here we go. Duck goes quack. What is more likely, finding life in our solar system or finding life up to 100 light years from Earth? That's a great question. I know someone say like I always say like everything's a great question, but like I choose the questions because they're great questions, and so I know they're a great question. Like I understand it's redundant. Like if I've chosen the question, then it's going to be a great question because I like the best questions. But anyway, right. So we're searching for life here in the solar system, and at the same time, we're searching for life across the universe. Here in the solar system, we've got Perseverance going to Mars. We've got the Climate Orbiter sniffing the atmosphere for methane. We're looking for ancient fossils, stromatolites. We're probing into the briny depths of Enceladus and Europa and searching for some kind of alien bacteria that might be living here in the solar system with us. So far, all the attempts to find life in the solar system haven't turned up, although some of them had been inconclusive. There was the Viking landers, there was the Allen Hills meteorite, there was the possibility of phosphine on Venus, but still, nobody is super convinced that life has been found. But if we found life here in the solar system, like really conclusive life, like European space whales or a giant fossil even on the side of a riverbank, an ancient riverbank on Mars, it would be incontrovertible evidence. You would know for certain that there was once life on Mars, that there was currently life on Europa, that there are European space whales, whatever it is. Because and it would begin more and more missions, more astronauts would go. You would send paleontologists to Mars. They would be digging up in the dirt. We would be pretty certain that there was life there. So the advantage of the solar system is that we can be certain. Up to this point, we don't know if it's out there. People think there's places here in the solar system where there could be life, but so far there just hasn't been. For the rest of the universe, our methods have to change. So the one possibility is that we are listening for signals from extraterrestrials with SETI. We're watching for laser beams coming from other worlds. We're listening for radio signals. And with radio signals, there are certain frequencies of radio signals that if you heard on one of those frequencies an artificial signal, it would be a dead giveaway. There is no natural way that we know of that a neutron star can provide a signal on the spectrum. So that would tell you for certain that there's life. But every other possibility is going to be inconclusive. And I've been feeling like one of the techniques is going to be, we're going to use our big telescopes. We're going to look at the atmospheres of exoplanets and say, okay, are there the chemicals in the atmosphere that could be given off by life? Astronomers call these biosignatures. And we've learned from the whole phosphine discovery on Venus, or non-discovery, that sensing these chemicals in the first place and confirming that they're there is actually really tricky. And, imagine how much harder. I mean, like, you've got Venus. It's right there. It's a huge planet. We've got big telescopes. They're not very far, and they could just barely detect the signal of some kind of life on Venus. When we're going to be taking the James Webb or these various, the aerial telescope, or these bigger, the HabEx, and trying to scan other worlds, there may very well come up. I wouldn't be surprised within a decade that these systems come online, that someone says, we've detected methane on a planet, on an Earth-sized world orbiting a sun-like star. But it won't be conclusive evidence. People will argue, and we won't know for sure. For decades, hundreds of years, until you can actually send a spacecraft, you can't know for sure until you can communicate. So I think I don't think we'll know either one. I don't think we'll keep chasing life here in the solar system, and it'll be hard to build the case that life was ever here. And we'll keep scanning the universe for life, and we just won't find something that's super convincing. So it's going to be tough. It's going to be hard, and it won't be a slam dunk. It won't be case closed. Just prepare yourself for, we think we found evidence, maybe astronomers have confirmed, astronomers are speculating. That's what the future holds. Dato Pharmaceutical, also laundry and tan. I'm serious. That is the username. You'll see it when we post the QA. Can you use special suits, exoskeleton, to simulate gravity? I get this question a lot, where we talk about how being in microgravity is bad for the human body, and that you need to have, right now astronauts have to work out all the time. And so one possibility people say is, well, could you just wear some kind of suit that resists, and it feels like it's magnetically connected to the ground, and every step that you take, it's pushing against you, and it makes it feel like you're in gravity. And I think that would be a benefit just for the kinds of activities that we want to do, where we just want to stand at a desk and we want to walk around and sit in a chair. You can imagine if you had some suit that was attempting to mimic gravity, that would be helpful, and it would definitely help with some of the muscles and some of the other issues that you'd be facing. But part of the problem with microgravity is that we have all of these inner problems. There's problems with your eyesight. There's problems with fluid redistribution around your body, and you need to have gravity to fix those problems. So a suit, although it would help with some of those, wouldn't help with a lot of the bigger problems. And we just don't know what the long-term issues are over years. So I think we're going to need to generate some kind of artificial gravity. That's the solution. Garth T. Would it be possible to collect water from somewhere in space and boil it as propulsion? It would be obviously no good to get to space, but if the ship is already in space and so is the water, is it worth using? Absolutely. This is actually a propulsion idea that is being considered right now by a bunch of people. It's called a steam propulsion system. And literally, you take water, you boil it inside the spaceship, and then you blast the vapor, the steam, out the end of the rocket, the steam rocket, and it works like a rocket, and it works well. And it's crude, like you're not having the incredible pressures and temperatures of a Raptor engine, but you're scooping up water ice, you're boiling it inside your spaceship, and you're blasting it out the back of the spaceship, and it's giving you propulsion. So it's using a resource that's very common. And so, yeah, this idea has been, so do, put some links, but look for a steam rocket. And in fact, you can build water rockets, bottle rockets here on Earth. So clearly that works. The other idea that's being tested out, and actually NASA is in the process of developing a mission that's going to try this out on a CubeSat, is they're going to take water, they're going to use electrolysis to separate the water into the hydrogen and the oxygen, and then they're going to recombine them like a liquid hydrogen oxygen rocket, and then use that to create thrust that's going to come out the back of the rocket. So there's other ways that you can use hydrogen and oxygen. Really, water is the key. If you can get your hands on water, it unlocks all kinds of advantages in space. So I think it's going to be the way to go. All right, so those were the pre-questions that I had. So now, absolutely, let's get into this week's questions that you're asking me live right now. Okay. Whoa. Apologies, just sort of catching up on all the questions here. Okay. Essay. With optical interferometry, could you build a space telescope in installments and with less demanding requirements regarding the size of the launchers? For those of you who don't know, optical interferometry, or interferometry, is where you take the light from multiple telescopes and you combine it so that they act like a big telescope. But it's not just that you're adding the light. Like, say you had 5 1-meter telescopes and you added the light. It's not that you're getting the equivalent of 1 5-meter telescope. That's easy. That is just, you can absolutely add the light from 5 different 1-meter telescopes, and that gives you the equivalent of a total collecting surface area of 5 meters. But what interferometry lets you do is it lets you separate the telescopes so that when you're receiving signals from, when you're looking at light, your telescopes are acting like a telescope that is as big as the separation between them. It's called the baseline. And so if you take 2 1-meter telescopes and you separate them 5 meters, it's the equivalent of a telescope that is 5 meters across. And that's way bigger than 2 individual telescopes. It's, I haven't done the math, pi r squared. Anyway, it's an enormous surface area of a telescope. You get high resolution, so it's really good for bright objects like quasars or the sun or things like that, but you don't get a lot of sensitivity, so it's not good for faint objects. And the wider apart you put those telescopes, if you move the 2 telescopes a kilometer apart, then they act like a telescope that is a kilometer across, but it can only see very, very bright objects. You can't see dim objects, but with incredible resolution. And so that's why the Event Horizon telescope, which imaged the event horizon of the black hole at the heart of M87, used the entire, telescopes around the world. It pretended like it was a telescope the size of planet Earth. The radio telescopes work well because the wavelengths of radio, the trick is that you have to align your telescopes so that they are perfect, that they are essentially receiving exactly the same wavelength of photon, the exact same photon. And so, for example, when you've got radio waves, the photons can be centimeters long, meters long, kilometers long eventually. And so it's very easy just using clocks. You're both pointing at this object, you're receiving all this data, and you're going, okay, look at the data, check the time, and then you match up the wavelengths, and boom, you've got your telescope. You do it after the fact on computer. With visible light interferometers, like the Very Large Telescope, you have to do it live. You literally have to take the telescopes, sort of move them a little farther, a little closer, until essentially the wavelengths line up and you're getting perfect interferometry between those two telescopes. Down to the nanometer, right? Down to the 100 nanometers when you think about the wavelength of different colors of light. So one of the ideas is absolutely to fly spacecraft in space, have them align themselves, and then in space, it's very easy to keep things exactly the right distance apart and make tiny adjustments as there's gravitational interactions with them. And so, in theory, you can launch multiple telescopes, have them be a certain distance apart, have them act like an interferometer, and you would be able to have a telescope that acts like a 5-meter telescope, a 10-meter telescope, a 50-meter telescope, a 100-meter telescope. But there's a lot of technical unknowns about launching these spacecraft, having them align with each other, maintaining alignment, combining the light, being able to download the light in a way that you can use on Earth. So there's been proposals to do this. There was a mission called the Terrestrial Planet Finder that never flew, but it was sort of like the greatest mission in my opinion, because it would be exactly that. There's going to be a gravitational wave observatory called LISA that's going to do that, but it's going to be an interferometer. It's going to be getting the spacecraft perfectly aligned with each other, but in this case, it's shooting lasers back and forth to detect gravitational waves. So, an interferometer makes a ton of sense, more sense in space, but of course, sending things to space is more complicated and expensive. So, there you go. All right. Professor Newman. Where are the moons of Jupiter relative to the magnetosphere of Jupiter? Would a Jovian moon base get shelter from space radiation, or be left out, or pass in and out, getting fried by the Van Allen belts? Sorry. Always have water. Okay. The moons of Jupiter are largely in the radiation belts of Jupiter. As you get farther and farther away from Jupiter, out when you think about the way the moons are aligned, you've got Io, Europa, Callisto, Ganymede, and Io is just heart of the storm. Europa's bad. Callisto's bad, but not as bad, and Ganymede is far less dangerous. But no matter where you are in the Jovian, literally no matter where you are in space, you're going to be eating radiation day and night. So you need protection. You need to be under the ice. But you don't need a lot of ice. Like a meter of ice. If you could get under, put a meter of ice blanket over top of you and your space colony, then you're protected. You're fine. So I think that's all you got to do, is if you can just dig underground, dig under the ice on probably Ganymede. That's my favorite. Ganymede, as I've mentioned before, Ganymede is the new Europa. Go to Ganymede, dig under, because it's got a magnetosphere. It's got lots of ice. It's the right place to go. And dig under the ice and you'll be safe. See. Oh, it's a good question, Arjun, but I don't know all the deep specifics. Okay. Samurai Hash. Do you think public funding can help get some large-scale space projects started, such as spinning habitats? Rapid as progress is, it needs to be faster. That's what a government is a public funding. When you look at things like, artificial gravity, like the Nautilus X mission, I think the budget that I saw for that was like $1.4 million. And it was like this big toroidal ring that would sit on the side of the International Space Station and, and spin around and provide the astronauts some kind of artificial gravity. And it was in the multiple billions of dollars to install this thing. So, like, you can't do a GoFundMe or a Kickstarter to raise that kind of money. There have been much smaller missions that have been proposed. The Russians, like 10 years ago, wanted to build a tiny little artificial gravity chamber for mice. And they were rats, and they were going to launch it, and it was going to spin, and they were going to see how it did for the rats. And then they'd been in space for some length of time, they're going to bring them back and see what this had done to their bodies. And there isn't really even that kind of level of testing that's going on. I mean, right now, the opinion is none, that nobody is actively planning to build any kind of long-term artificial gravity. And I think the reason is because for the state that space exploration is at right now, it's not necessary. Like we know that Scott Kelly could spend a year in space and he was fine. I mean, he was definitely weak when he got back to Earth, and he definitely had to build up his muscles, and he was feeling nauseated and lots of problems with his blood pressure and all kinds of things. But still, he was able to bounce back from it, and now he's fine. So, I mean, you could probably go longer. You could probably go to 2 years, or maybe even 3 years. And at a certain point, it's going to start getting dangerous. But I'm sure we're going to test out the limits of that. And when you think about the kinds of missions that are going to happen, you're going to have astronauts going to the International Space Station, astronauts going to the Lunar Gateway, astronauts going to the surface of the moon and on to Mars. At no point is anybody living in space for any long period of time. And so I think for the long-term horizons, we definitely need to know how to counteract microgravity and how to produce artificial gravity. But we don't have like a purpose for it, a need for it. It's a nice to have. It's not a need to have. Instead of building and operating a very complicated multi-billion-dollar centrifuge on the International Space Station, you send a treadmill and some weights, and they work out. That's the strategy. So I think that, I mean, obviously we hear about people like the Gateway Foundation are planning to build a gigantic O'Neill cylinder, or like a, some kind of ring that's going to, they're going to dock starships to, and so on. And who knows what's going to happen once Starship truly starts flying and things that used to seem like incredibly expensive start to become reasonable. But for now, although it's a big unknown, and although it is sort of the great stumbling block to inhabiting space, it's like the one thing that we can't fix so far. There's no huge priority to do it, and so no one sort of keeps putting it to the top of their queue right now. But eventually, I'm sure someone will sort it out. All right. Ted Krause, your thoughts on Bezos putting his satellite in space like Starlink? If you think Starlink is the beginning of satellites in space that are providing telecommunications to Earth, like this is just the beginning. Yeah, Starlink is going to launch 42,000. Amazon or Bezos, Blue Origin can do their version of it. The Chinese are going to have their own version. The Russians are going to have their own version. Other countries are going to have their own version. Like, this is over. There's going to be a lot of satellites. And on the one side, as we keep talking about this, right? Starlink is kind of amazing. And in fact, Starlink, they announced they're going to come up with a cheaper version. They're going to probably be doing a cell phone version. In a few years, and it won't be long, you are going to be able to receive satellite signals on your phone anywhere on Earth all the time. And it's going to be almost free. That is the future. That's where this is all going to go. and it might be 10 years, maybe 20 years. 20 years, you will have a device that is connected to the satellite internet that allows you to go anywhere on Earth and have as fast an internet connection, well, twice the water. All right. And have as fast an internet connection as you could possibly want. And it's going to come from tens of thousands of satellites by multiple providers competing in space, launching all the time. That's the future. And it sucks. And it's great. We're going to, for us, people are always nervous about like we're going to lose the night sky, but we're not going to lose the night sky. I guarantee you can go outside and look up and you wouldn't be able to spot a Starlink or an Amazon link or a OneWeb or whatever. You wouldn't be able to see any of them. They're just too faint for the vast majority of people. You got to have really good conditions, really good eyesight. It's got to be really dark. It's got to be the right time of year. You got to be at the right latitude for you to be able to see these things. So for regular people, it's not going to happen. And we've lost the night sky. If you are sad about satellites, you should be furious about light pollution. Like, the thing that has stolen the night sky from all of us is people leaving their lights on outside in cities. That if you have never been to a truly dark sky place and seen the Milky Way with your own eyes, then you don't know what you're missing. It is transcendent. And so satellites are going to be nothing compared to the damage that's already been done to the night sky. They're going to be imperceptible. The thing that's going to be paying the price is astronomy. The big telescopes, the observatories, they're the ones that are going to be losing the night sky. And it's not going to be like suddenly telescopes don't work. It's just going to be night after night after night. They have to pull satellite trails out of their images again and again and again. And so like it took you one night to do your observations, and then it's going to take 2 nights to do your observations. Then it's going to take you 5 nights to do your observations. It's just going to get, it's just going to be an ordeal. But that is the price that we will pay for a magical satellite connection that allows us to communicate with the world, and for billions of people who were never able to connect to the internet will now be able to connect to the internet. So welcome to the future. But again, if you're in any way, shape or form grumpy about what these satellites are going to be doing, then take action about dark skies. Help preserve dark sky locations. Help, you talk to your city about switching out the lights so that your city produces less light pollution. That should be your priority. Like, take all that rage and channel it into fighting for dark skies, just in general, because that's already been taken away from us. Okay. John Seffield asks, can rogue planets be made without the help of a sun? We think so. Like right now, when you think about how a star is born, you've got this primordial gas, hydrogen, and dust left over from the Big Bang, and something triggers the star cloud, the gas cloud, to collapse, and it turns into a star at the center, and it's surrounded, and then the star, as it, they always like the skater spinning, right, pulls in its arms, the star closes in and spins up faster and faster and faster, and then you get this accretion disk forming around it, and then the planets form as knots in the accretion disk, and then the star really ignites and blasts out the radiation and clears out all the material that's in between. You're left with a star with planets orbiting around it. But we now know that there's tons and tons of these brown dwarfs all over the place, and so they are just smaller versions of stars. So imagine you've just got a smaller version, and you've got this brown dwarf at the center, and it spins up fast, and it gets this accretion disk around it, and then it's putting out sort of feeble radiation. Maybe it doesn't even clear out the dust in the accretion disk. I don't really know. And so it's going to, brown dwarfs will inevitably have planets orbiting around them. And the rogue planets are just a smaller version of that. So imagine you would have like a Jupiter's worth of gas and dust that collects together into a planet, and then you've got it just sitting there. And now it really looks like the world is spiders, right? The world is really just spiders. Like we think we're the life, but really it's, wherever you are, there's spiders all around you. Well, it's probably that way with rogue planets. I've heard anywhere from 1 to 10 times as many rogue planets as there are just regular stars and regular planets in the Milky Way. So in fact, there's going to be tons and tons of them out there. And what's really interesting to me about rogue planets is they kind of change our concept of what what it would be like to explore the Milky Way. Because we sort of imagine, if you want to go to another star system, you've got to leave your star, you've got to be able to fly to Alpha Centauri. It's a 4 light year journey. But if there really are 10 times as many rogue planets just wandering around throughout the Milky Way, then in fact you only have to be able to make it like a tenth. You only have to be able to make it like a tenth of the journey. Like you don't have to go very far. So, and then you could set up at one of these rogue planets and harvest the resources. There's going to be ice, and maybe you're going to have a gas giant with ice moons orbiting around it, and you could use this as a pit stop. And so, in fact, exploring the Milky Way could potentially be a lot easier than we thought, because there's just, imagine there were 10 times as many gas stations as you thought. I love it. All right. Okay, I see what's happening here. All right. Okay. Sean Marson asks, hey Fraser, if we used a light sail to go to a nearby star, I know there's the problem of how to stop. Couldn't we flip the sail around halfway there and use the pressure from the destination star? No. So to get a light sail up to the kind of velocity, well, I guess it depends on how fast you're going to go. Man, choky. All right. So it depends on how fast you're going to try to go. So when we're talking about like the idea of the breakthrough starshot, right? You've got these tiny little spacecraft that are being accelerated by a big, powerful laser. And they're going to be accelerated to 10% the speed of light. And then they're going to make the journey across space. 40 years, they're going to arrive at Alpha Centauri, and then they're going to do a flyby through the Alpha Centauri system, take a bunch of pictures, send them home, and then they're out into space. Like a super Oumuamua. If you went a lot slower, then in theory, you could use the starlight to slow yourself down. But you've got to get really close to the star, because you were accelerated by a laser. Now, if you were only accelerated by the light of the sun, then you could do the reverse. If you only accelerate with the light of the sun, then when you get to the other star system, you could decelerate from the light of the sun, and you could slow yourself back down. I forgot to record. Chat's going to kill me. Okay. Anyway, you could decelerate yourself with the light of the sun, and you would be able to go into orbit. But as long as you accelerated yourself with a laser, unless you have a laser at your destination, you're going to be going too fast, and you're going to just go on a hyperbolic orbit through the star system, and you're never coming back. So if you're willing to go slowly, then you can slow yourself down when you get to your destination. But if you want to go fast, there's no way to slow yourself down. Sorry, Chad. I totally forgot. It's okay. That's why we've got the YouTube version. It's not quite as good. All right. Shay Whelan. How far will we see with the new James Webb scope? Of course, get all your jokes out about James Webb. James Webb is launching on October 31st, 2021. We are 9 months away It is going to launch. It is going to happen. Right. But let's so get that out of the way. What will we be able to see with James Webb? Now, I mean, James Webb, like to ask like how far can you see with the telescope? It depends on what you're looking at. James Webb will be able to see dwarf planets here in the solar system. James Webb will be able to see the atmospheres of exoplanets orbiting around other stars. So it'll be able to do the kinds of things that telescopes already do all the time, just better. But like, what's the farthest thing James Webb is going to be able to see? And right now, when you use the Hubble Space Telescope, like when you think about when Hubble did the Deep Field Survey, what they did was they took Hubble, they pointed at one region in Ursa Major for hundreds of hours and just stared and stared and stared, and then just collected every single photon that they could see. And using Hubble, you can get out to like 1 billion years after the formation of the universe, after the cosmic microwave background radiation. But you can't really see a lot farther than that. But there's a few tricks. If you use gravitational lensing, where you've got a foreground galaxy and you've got a background galaxy, and the light is coming from the background galaxy and it's going around the foreground galaxy, then the foreground galaxy acts like a lens for the object that's a lot farther. And what you get is you're able to literally, the front galaxy acts like a telescope to show the farther galaxy. And so using that technique, there's about, I think there's about 1,000 known gravitational lenses, and each one gives you this view of a galaxy. And so you've got these tiny little pinholes in the universe where you're able to, every now and then, there's like as far as Hubble can see, and then every now and then there's these little spots you can see, farther. Now you're seeing 500 billion years after the universe began, or 250 million years after the universe began, but only in very specific locations where the galaxies line up perfectly. James Webb will just do that anywhere it wants, just raw power. You point James Webb at any spot in the universe, stare long enough, and you will be looking all the way back to almost the beginning of the universe, the time when the first galaxies were coming together. But there's a little bit farther that astronomers really need to see. And so, when you think about that, you're looking all the way out to the time when the big galaxies are coming together. But earlier than that in the universe is the time when the first stars were forming. And right now, we don't have any technique beyond maybe radio waves to be able to detect those first stars forming. And so there's a future, like LUVOIR. When LUVOIR launches, it'll be like an 8 to 15 meter telescope. It will be able to go all the way to the point that the first stars were forming in the universe. Literally the first time the universe lit up after the cosmic microwave background. That's one of the reasons why LUVOIR. And there's another space telescope that's in the works called Origins, which will be kind of like a super version of James Webb. It'll have, I think, it'll have like a 9 meter telescope, but it'll be sensitive to the infrared and the way that James Webb is. And it'll also be able to look out to those first stars that are forming after the beginning of the universe. So James Webb will, just through raw power, be able to go all the way to see the stuff that Hubble needs to do these kind of bank shots to see. And but then follow-on telescopes will be able to go right out to literally the beginning of everything. All right. Arjun, could gravitational lensing be messing up our data concerning the microwave background radiation, like the age of the universe, etc.? Gravitational lensing. So we talked about gravitational lensing just a second ago here. And so would that be messing up our data? You could see, I know that astronomers can see the cosmic microwave background through the gravitational lensing that they do, but they can sort of adapt and adjust for it. In fact, there's some really interesting research that's being done using quasars. So what astronomers will do is they will use like distant quasars that are shining through just the intergalactic medium, just the gas and dust that is just out there in space. And the way the dark matter blobs and the way the galaxy cluster blobs sort of work, they can cause this gravitational lensing, and they can help reveal the distribution of gas and dust that's out there in the universe in between galaxies. And this technique has been used to find the missing matter in the universe. Not the dark matter, but the missing regular matter. But I don't think that gravitational lensing causes that big of an issue for observing the cosmic microwave background radiation. That's been dust is the problem for viewing the CMB, not gravitational lensing. There was like a really interesting piece of news that came out like today when I'm recording this, which was that astronomers have used pulsars to potentially map the primordial gravitational waves, essentially the background gravitational waves of the universe, because pulsars act like incredibly sensitive beacons that you can measure the distance that light is traveling, because they're so regular. And so as gravitational waves are rolling over these pulsars, the pulsars are sort of shifting back and forth in space. And so astronomers have been observing pulsars for like a decade very carefully. And they think that they've been able to detect the evidence of background gravitational waves as sort of, if you can imagine these pulsars like buoys sitting on the water as waves are rolling up and down, and you can detect them sort of shifting back and forth. And if that's true, that's really exciting. That's way ahead of when most people were going to predict that we would detect primordial background gravitational waves, which is kind of exciting. So I'll keep you posted on that. Now, totally unrelated to R. Jones' question, but I just needed to shoehorn that in there. All right. Chris Sender asks, any plans for the Titan drone to photograph one of the oceans? In case you missed it, we had one of the researchers from the Titan Dragonfly project on the weekly Space Hangout this week. So if you're looking for like another thing to watch that has me and a bunch of other space journalists, you should totally watch that. So this is really, I'm answering this question to give you a shameless plug for the weekly Space Hangout. Check it out. Upcoming interview with Avi Loeb. Upcoming interview with the showrunner for Stargate. But no, the Titan Dragonfly probe is, of course, this incredible, it's a hexacopter with a nuclear battery on board. It's going to be flying around in the skies of Titan, observing this world. Will not be able to go anywhere near the seas. The seas are at the poles, and Titan, the Dragonfly, is going near the equator. And the main reason for that is so that Dragonfly can communicate with Earth. So if it goes up near the poles, it's really difficult for it to be able to communicate back home with Earth. So unfortunately, there are no plans to send Dragonfly anywhere near any of the poles to collect any of that information. That said, like the RTG on the Dragonfly is going to last forever. Like think about Curiosity. 2012, Curiosity landed on Mars. So we're closing in on like 9 years since Curiosity has been there. The Voyager spacecraft, like we're still getting signals from the Voyagers. I mean, sure, they couldn't probably operate a hexacopter in a Titan environment, but still, we should see that thing operate for a long, long time. So stay tuned. But you're going to need a little more infrastructure. You're going to need some kind of satellite, probably a polar satellite that's orbiting around Titan that can act as a relay satellite to send signals back to Earth. And then you probably want like a submarine or a sailboat or something to be able to really explore. Submarine's the right machine. So you send a submarine orbiter combo to Titan that delivers the submarine into the polar seas, and then the orbiter is retransmitting the data back up to space. One of the really cool things about those seas, I know I'm completely going off in tangents today. One of the really cool things about those seas is that they are pretty transparent to radio signals. So normally water is the worst. You need a technology like sonar, or you need some kind of tether, and then you communicate from the tether. But liquid methane is actually reasonably clear, and so you could actually communicate from your submarine up to space, no matter where it is, and to be able to retransmit those signals. So yeah, come on, let's get on with the Titan submarine. All right, I'll answer this question because people ask. Adhesive wombat. What is your astrophotography setup back there? That is a 80 millimeter apochromatic refractor with a black and white CCD chip, but I've removed the camera and I've put a eyepiece on it, visible eyepiece. And so we take it out whenever something really interesting has happened, like when Mars got to its closest point, when Jupiter, Saturn, and it's fine. It's a good telescope. The mount is very heavy, and it's a pain in the ass to use. So, as you probably know, I have access to a much faster, much better telescope, thanks to Oceanside Photo and Telescope in Landers, California. So I've got this amazing telescope with a really fancy mount and a really fancy camera that I can use anytime I want, from in the house. So mostly that thing collects dust. I don't recommend getting unless you're serious about astrophotography, I don't recommend getting a telescope like that. Like for most people always ask me, like, what telescope should I get? Get a Dobsonian, 8-inch, no bigger, no smaller. Just get an 8-inch. Yeah, but yeah, no, I feel bad. It collects dust. All right. Eric One asks, what type of radiation is Jupiter emitting? Jupiter is emitting, well, I guess Jupiter is emitting infrared radiation. It's kind of warm. It emits a little bit of X-ray radiation from the various auroral events that are happening at its poles. But the big magnetosphere that's around Jupiter is the same kind of magnetosphere that we have around Earth. It's made of trapped radiation. So particles from the sun, the solar wind, are passing through the magnetic field of the global magnetic field of the planet, and they just get caught up going around in orbits around the planet, and they get concentrated. And so we have one with Earth, and Jupiter has one that's like 20 times more powerful. Saturn has one. Just wherever you get a magnetic field interacting with a stream of particles coming from a star, you get a very dangerous radiation environment. I haven't seen Tenet yet. Oh, good question. All right. Jay McDonald, with Blue Origin's continued success and no commercial operation, do you think that Blue Origin is a serious industry contender or a billionaire pet project? Love your content. Is Blue Origin a contender? Probably. I think that Blue Origin is a contender. At this point, Blue Origin has probably been operating longer than SpaceX has. I don't know the actual date that Blue Origin started. Of course, their logo, their saying is like progress ferociously, gradual progress ferociously, something like that. And so they're going very slow and steady, and they're not having the dramatic crashing starships like we saw with SpaceX. We see just every few months another New Shepard launches, lands safely, works perfectly. So are they a serious contender? Well, so there's two parts to Blue Origin, right? There is the rocket engine part, and that's very successful. They've already got customers for their methane, their BE4 rocket engine. They're going to be on the Vulcans. There's probably going to be other people that are using it. It's sort of like it's a way to replace all of the Russian, Ukrainian rocket systems that are being used in America with home-built versions. So I think we can safely say that the rocket engine department of the company is doing great. But what about the big launchers like the New Glenn? Well, in theory, the plan is that we're expecting to see a New Glenn test probably sometime this year. And it's all been secret, but we've seen some hints. We've seen them picking up their own facilities, their own landers, their boat. They've bought an old cargo boat to land the rockets on. We've seen what the launch fairing looks like, and it's big. And when you look at the capacity of the New Glenn is going to be a monster. Like it's bigger and more powerful than the Falcon Heavy. So it's not going to be as big and as powerful as the Starship, and it's not fully reusable. So I don't think that if Starship works as planned, Blue Origin, New Glenn won't be able to compete against that, because you just can't compete against a fully reusable rocket. But if Starship has some problems, or New Glenn works well, or they're able to figure out a fully reusable version of it, and I'm sure they are, then it'll be a serious contender. And of course, they can always just copy SpaceX. They can always just do the same thing that SpaceX does. Have their own version of stainless steel New Glenn. Maybe that's what the new Armstrong will be. So I think that, and Jeff Bezos' money is bottomless, like just bottomless. Like, you just keep spending money year after year after year to get this right. So yeah, I think that Blue Origin will be a serious contender to SpaceX. But there's so much to be said for SpaceX just testing and rapidly iterating, and that's why I feel like you see this really rapid pace of development coming out of SpaceX and Elon Musk, is this understanding that the competition is going to be hot on his heels, and they need to sort this out and corner the world's launch industry as quickly as possible. I think Elon Musk also, of course, is thinking about existential crises, artificial intelligence. Although you can't run from aliens or from artificial intelligence to Mars, Elon. They'll chase you there. Or global pandemic or whatever, right? So I think that there is a sort of a hustle, there's a sense of urgency that is in SpaceX that is not in Blue Origin. And yet that sense of urgency is in Amazon. So it's weird to me that the same guy who runs both companies doesn't have the same management style. So anyway, we'll see what happens. But yeah, I think I give Blue Origin a 50-50 chance of being a serious contender to SpaceX. But I think SpaceX, once Starship flies, they're going to run away with it. Like, fully reusable 2-stage rocket, nothing else will be able to compete against that. Let's see. Apologies, I'm just sort of looking through all a lot of good questions. I'll do some quick ones here. All right. Grumman Pilot 99. What's your telescope? No. Grumman Pilot 99. What is your telescope collection like? I have like 3 telescopes. I have the one behind me. I have like a little tiny Dobsonian, like a 4-inch Dobsonian. And I have a Galileo scope. And I've got a pair of astronomical binoculars. So I don't have a lot. I am thinking of picking up an 8-inch Dobsonian, just because I love Dobs. They're the way. Phil Deshane, if Earth was tidally locked to the sun, would the surface gravity be the same, less, or more? The surface gravity would be less. More. Okay, so right now, because the Earth is turning, when you're standing at the equator, you experience the gravity that's pulling you down towards the Earth, and you also experience an outward force from the rotation of the Earth. But it's minor. It's like a fraction of a kilogram. But if the Earth was tidally locked to the sun, there would always be facing one side of the sun. It would effectively be not rotating, and so you would become a little bit heavier. Mitch Harpino. With missions to the moon in the future, are there plans to build some sort of telescope on the moon? Nothing official. There are no specific plans, but there are some really interesting ideas to build a telescope on the moon. The one that I like the best is to build a radio telescope on the moon, where you essentially land a spacecraft, it deploys a rover, the rover rolls out from the lander, deploying wire onto the surface of the moon in this big, huge pedal formation, like kilometers long. And then it returns to the site and then does another shape. And so it deploys these little detectors all the way. And then you could create this gigantic radio telescope on the far side of the moon that is safe from radio traffic on Earth and would allow us to see like right out to the beginning of the universe. It's a great idea. Not that expensive. It's the perfect place to do it. So I hope that's what we see first. Apologies. Okay, we'll do one more. Citizen Case. Is it Casey? Citizen Casey. I think that's what it is. Citizen Casey. If we receive a signal such as the WOW signal, can we be sure where it came from, considering star drift and our own wobble within our galaxy over the thousands of years from the signal travel? Yeah, you can. I mean, although definitely the signals take some period of time, like let's say our Alpha Centauri takes 4 years for signals to get to us. You know, the farthest we can reasonably detect a signal from an alien civilization is like 1,000 light years away if they're like pointing a coherent beam of radio waves right at planet Earth. And 1,000 years, stars don't move very much. Like over tens of thousands of years, hundreds of thousands of years, stars are moving in the sky. But 1,000 years, like a teeny little bit in space. So I wouldn't worry. We know which star was sending the signal. All right, reached the end. So I'm just going to record a little outro bit, and then I'm going to stick around. So don't go anywhere. All right, I'd like to thank, let's do this. Okay. So thanks to all our patrons. Thanks to John Sears, The Mysterious Mark, Ert O'Hara, John Grigg, Karsten Nielsen, Andrew Hudson, and the rest of our 855 patrons for their generous support. Want our videos early with no ads? Join our community at patreon.com/universe today. If you want a single comprehensive resource for space news, you'll want to subscribe to my weekly email newsletter. Every Friday, I send out a magazine of space news with dozens of stories, pictures, brief highlights, and links you can find out more. Go to universetoday.com/newsletter to sign up. It's totally free. And did you know that all my videos are also available in a handy audio podcast format so that you can have the latest episodes as well as special bonus material like interviews with me show up on your audio device? Go to universetoday.com/audio or search for Universe Today on iTunes, Spotify, or wherever you get your podcasts. And I'll put a link in the show notes. Thanks to everyone watching here and on Twitch, and to everyone who asked a question. If you want to ask a question for an upcoming show, you can post it in the YouTube comments or on Patreon, or you can join me live on my YouTube channel every Monday at 5 p.m. Pacific Time. Thanks to all the moderators, and a special thanks, as always, to Chad Weber, Nancy Graziano, and we'll see you next week. Okay. Awesome. All right, so I'll stick around for another like 15 minutes or so, and then I got some television to watch, I think. Gotta catch up on the Stargates. Yeah, Vistotuti says there was a signal from space, but the ancient Greeks missed it. Yeah, can you imagine? That would suck if really interesting signals were sent in the past and we just didn't have the technological capabilities to be able to answer it. Powell Sersky, can you share a bit of the strategy for Avi interview? What new can we expect other than other channels already did? Any hard questions? Um, yeah, well, so like I'm not interested in talking to Avi about whether or not Oumuamua is an alien spacecraft. So that's like I think that might be different, right? Like at all. No part of me, because like I already know, I know what he thought, and I know what his evidence is, and I know his evidence is, circumstantial. He's really convinced, and I'm sure he'll be very, but we can't test it, we can't follow up, and so that's not super interesting to me. What's interesting to me is like for the first time we've got a really respected researcher. Avi Loeb is at the height of power and authority and capability, and is sits on many of the really important astronomy committees and helps guide funding and helps make or break new researchers. And up until this, just the hunt for extraterrestrials, the hunt for intelligent life in the universe has been considered a no-no. And no, like SETI the SETI Institute, like the poor SETI Institute has had to be a completely private agency. They've had to do fundraising, like they've had to do GoFundMe's about to be able to get radio telescopes so they can search the skies for aliens. And yet finding aliens is the most important question we can ask, which I always say. So I'm interested to kind of find out where that balance is now. Like, does making such a bold claim help with funding? Is it going to achieve his goals? Is it going to help in the search for life in the universe? Because like that's a through line through everything he's doing. He, on the one hand, is quite into like black holes and helping figure out event horizons and doing really fundamental research. And then on the other hand, he's interested in finding out whether or not fast radio bursts come from aliens and things like that. And so I think that's important. And that's what I'm interested in is like, I want more research done into aliens, into extraterrestrials, into SETI. And but I don't want it to be like the moon landings where people were really excited for a while and then they stopped. And I think that's the problem. So, so that's the kind of conversation that I'm interested in having with him. And I'm also really interested in, I think he walks a really great balance between thinking of really out there ideas. Like he's done a ton of really incredible work. He's done papers about like a time when the entire universe was habitable. 8 million years after the Big Bang, the entire universe was the temperature of was the temperature of room temperature, which is amazing. So yeah, so I'm kind of excited to just to talk about that and like how can we help people be creative as scientists and be able to reach larger audiences and at the same time be scientifically rigorous and help encourage sort of just a larger scientific knowledgeability by people. So that's the kind of stuff that I want to talk about. So I know that's totally different than, so you're saying that Oumuamua is a solar sail. What's a solar sail? That kind of thing. No, I'm not into that. I'm not having it. So hope that's okay with you. But that's the kind of conversation that I'm looking to have with him because I think that he can bring a lot to just like him, like David Kipping, Jason Wright, the way Carl Sagan did, the way Carl Sagan was able to do really good science and then at the same time unlock everybody's imagination about what might be out there in the universe waiting for us. And that's what I want to see more of. Um, let's see. Yeah, so yeah, people are saying skip the questions. Cypercharge. Any updates on your experience with your Starlink internet connection? No, it's the same. I haven't been using it actually much because I got it as a backup, and my regular internet is really good. But when I need it, I'm gonna need it. So I should be doing more testing. I should be like putting it in different parts of the property, figuring out where it gets blocked. Like I know that the best place for the Starlink satellite dish is to be sitting out on the sidewalk in front of my house, but clearly that's it's a bit of a risk. So do I take the thing and put it out in the lawn as far away from the trees as possible and then put it inside at night? I'm not sure. Anyway, so yeah, my property is sort of like where it is right now. The part that's kind of, I've got like a fence around the house, and so the behind the fence, it's kind of locked in, and there's like trees all around, and there's the house. It doesn't have a really good view to the sky. So yeah. All right, I think I'm gonna wrap it up. So thank you everybody for hanging around today. I really appreciate it. Thanks for all the great questions. That was a lot of fun, and we will get to work on processing this. I'm not sure what the next interview is. Then I don't have. I thought I had a double interview with Abby Lowe, but now it turns out I don't. Just the one. So I will. I'll find another. I'll find someone else to interview. There's a. I kind of want to talk to the people about the gravitational wave, background gravitational waves and pulsar. So maybe I'll see if I can coordinate that as an interview. All right. So thank you, everybody. Really appreciate it. Thank you, of course, to Chad, Nancy, all the moderators, everybody watching live. This is super fun, and we'll see you all next week. Thanks, everyone.